Okay, in this section we're going to talk about another phenomenon we can see upon stratification called statistical interaction or effect modification. And the assessment strategy, at least in terms of how we're working now, is similar to that of confounding. It's the same idea, but what we see upon stratification will be different. And again, just to really hammer the idea over your head to start, we'll start with a fictitious example that has some extreme results. Let's look at the results from a fictitious data set comparing two treatments for a fatal disease as the impact of each on reducing death. We're going to compare surgery versus drug treatment. There are 600 younger patients and 600 older patients in this random sample of 12,000 patients. Here's the data on all patients and their survival post-treatment, their 1-year survival post-treatment. And we can see if you actually go through this example numerically, the relative proportion of persons dying in both the surgery and drug groups is identical, which gives us a relative risk of death, an estimated relative risk of 1, an odds ratio of 1, and a risk difference. I didn't show it here, but P1 hat minus P2 hat of 0. So if we looked at everyone, altogether it appears there's no advantage of one treatment over the other in terms of preventing death. But let's look at the younger patients only. Here's the data on only the 600 younger patients. What turns out, if you look at this here, the relative risk of death for younger patients, surgery compared to drug amongst the younger patients, is 0.5. 50% reduction in death within 1 year for those who have the surgery compared to the drug amongst the younger patients. If we look at the odds ratio, it's 0.25. Now let's do the same thing for the older patients. We get almost exactly the opposite result. The relative risk of death for those who get surgery versus drug amongst the older patients, those who get surgery are twice as likely to die in 1 year as compared to those who get the drug. And the odds ratio is 4 to 1 odds. So just to recap the overall and age-specific results, when we looked at everyone altogether, there was absolutely nothing going on in the sample. But when we looked at those who were younger, it appears that surgery was preferable to the drug. The relative risk of death for surgery to drug among the younger patients was 0.5. However, when we looked at older patients, we got the reverse. The relative risk of death for those on the surgery relative to the drug was 2. So what's going on here? I didn't put in confidence intervals here, and we could consider uncertainty, etc. But basically what we're seeing here is that when we stratify by this third factor of age, we not only get results within each age-specific strata that are different than the overall association, but they're different than each other. In other words, unlike the scenarios we considered for the confounding examples, where when we stratify we got qualitatively similar results within each strata, here we get qualitatively very different results. In other words, if not accounting for sampling variability, but just given our estimates, it appears that surgery is preferable for younger persons and the opposite is true for older. Here what we have is the association between death and treatment was not only somewhat masked or obfuscated by age, but it also depends on age. And that's the idea of effect modification or interaction. When we stratify by the potential confounder and or effect modifier, we get results within our strata that are qualitatively different across the strata. In this situation, it would not make sense to mash these two stratum-specific estimates into what we call one overall age-adjusted association, because they're estimating two different processes. One is protective, the other is harmful. Why would we mash those two together to get one overall age-adjusted association? Here the lesson is that in order to properly characterize the relationship between the outcome exposure, between death and treatment, we need to first ask, well, are you looking at older people or younger people? Because the answer depends on which group it is. So the best thing to do here is keep these stratum-specific estimates separately and report two separate associations. Don't try and mash them into an adjusted single number because it doesn't make sense in this type of scenario. I'll give you a real data-based example that I think is interesting. And for those of you into environmental health, it's an interesting treatise, and it's based on data from the United States, from the eastern United States. The data on the elevation and the percentage of dead or badly damaged trees from 64 sites in the Appalachian region of the United States was collected. And the majority of the states, 56, are in northern states, and then the remaining 8 are in southern states along this Appalachian region in the eastern U.S. So we have information on a continuum from 0 to 100% of the percentage of dead or badly damaged trees at each plot. And then we also have elevation information about each site, and basically whether it was above or below 1,100 meters. So this is certainly an observational study. We can't randomize these sites to different elevation groups. We have to take them as they are. And this just shows you this is it listed in Stata. For each of the 64 sites, I have a number that quantifies the damage, the percent damaged. So the first site has 5% damage. And then the elevation group, which is actually a 0 or 1 variable, a numerical variable with a text label, and you're seeing the text label that gives the height group. And then similarly for the region, a 0 or 1, which has a text label. So let's try and assess the relationship between the percentage of damaged trees and elevation visually. And here's a box plot. And what do you see here? Well, if you compare the medians, it actually does look that there's something going on, that those at higher elevation tend to have lower median damage than those at lower elevation. But then when you compare the boxes, the middle 50%, there's much more similarity there. Now, there's a little more variability in the damaged trees in the higher sites, but the middle 50% is somewhat similar. But suppose we wanted to quantify this with a number and put confidence limits on stuff. Well, the best we can do is compare the means. And it tells a slightly different story than the medians. We actually look at the mean percentage of damaged trees across the sites stratified by elevation group. We see similar average percentage of damaged trees, 37.5 in the lower elevation sites, 37.7 in the higher. So this mean difference in percent of damaged trees for sites at higher elevation compared to sites at lower elevation is 0.2%, 0.2%. And if you put confidence limits on it, it certainly includes 0 and is pretty much equally balanced around 0, negative 18.8% to 19.2%. So at least using the mean as a summary measure, there is no statistical association. But remember, we also have information about the region. Check this out. This is just FYI. Here's a box plot of the percentage of damaged trees by region. And it's pretty clear from this picture that this outcome or percentage of damaged trees is also related to region. Has something to do with region. So at least considering the box plot, sites in the south have less damage. Now, if this region is also related to elevation, then it's possible that part of the relationship we originally saw or didn't see between damage and elevation is because of this behind-the-scenes thing going on with region. Here's just a potential Venn diagram for you. We saw almost no difference in the average percent of damaged trees between elevation groups when considering all sites. But now, to adjust for potential regional differences in the elevation groups, let's stratify by region and re-estimate the same association between damage and elevation separately for northern and southern sites. So let's look only at southern sites. There were not many southern sites, and only 2 of the 8 that we have were at lower elevation. But nevertheless, if we consider the mean difference between the elevation groups amongst only the southern states, look at this. Southern sites at higher elevation have less damage on average, 14.5% less on average than southern sites at lower elevation. That's a large difference in the estimate, but because we only have 8 observations and only 2 of them in the lower elevation group, we have a lot of uncertainty here. And the confidence interval is pretty wide and includes 0. It could be anywhere from 48% lower on average to 19% higher. So a confidence interval of negative 48 to positive 19. So even though the observed result is qualitatively interesting, we can't estimate it with any precision. Let's do the same thing for northern sites. And you can see here that while we do have more northern sites, the majority of them are at lower elevation. But it turns out that those at higher elevation have greater damage on average by an absolute difference of 23% than those at lower elevation. And while this confidence interval is wide as well, it does not include 0. It goes from 2% higher to 44% higher. Interesting. Let's just recap. When we just started and we ignored region, we pretty much saw no association between percentage of damaged trees and elevation. But when we stratified by region, well, the northern sites showed a positive, statistically significant association between damage and elevation. And the southern sites showed a negative, non-statistically significant association between damage and elevation. So it appears that the association between tree damage and elevation is different, both in magnitude and direction, depending on region. And we do have a small data set, so we have a lack of precision here. So the lack of the statistical significance of the negative damage elevation associations may be because of low statistical power, basically because we had very little information, so our standard error was large. So how could we rectify this? Well, we could. We did stratify, and we got two different estimates, and we could take a weighted average of them and get what we'd call a region-adjusted association between damage and elevation. But that doesn't really make a lot of sense, does it? Why combine estimates that differ in direction into one overall estimate? And a better approach would be to report the two mean differences in damage between low and high elevation sites separately by region. Just say, look, the process is different. At least our data suggests that, and we'll show you two estimates of this measure of association, one for northern states and one for southern. The beautiful thing about all of this is that we can also investigate effect modification and statistical interaction alongside confounding using the techniques of multiple regression, which is where we're going.